Hello friends, welcome to my lecture on undirected and directed graphs. Let us first define an undirected graph. An undirected graph G consists of a set B of vertices and a set E of edges such that each edge E belongs to E is associated with an unordered pair of vertices. Say for example, here you can see the vertex A. Okay, the vertex A is associated with the vertex B and the vertex C. Okay. So, and it is an unordered pair of vertices. So, we can write AB, the edge, this edge, okay, can be written as AB or BA, because there is no direction associated with it, and this edge which is by which A is associated to C can be written as AC or CA. Okay. So, the figure shown below is an example of an undirected graph. An edge joining the vertex pair I and J is referred to as either Ij or Ji. Now, on the other hand, a directed graph, or we also call it a digraph, consists of a set B of B equal to Bg, whose elements are called vertices, points or nodes. A collection E equal to Eg of ordered pairs of vertices called arcs or directed edges. So, here you can see the edges are directed, there is a direction associated with it. So, it is called a directed graph or simply edges. So, in the case of a directed graph, we have a set B whose elements are called vertices and a collection E of ordered pairs of vertices called arcs or directed edges. Say for example, in this figure you can see there are 4 vertices, okay, B1, B2, B3, B4. Okay. So, B is equal to B1, B2, B3, B4 and E is equal to. Okay. So, now you can see there is a direction associated with each edge. Okay. B1, B2 okay, is joined by the edge E3 and E3 is in the direction from B1 to B2. Okay. So, we have E3, let us say begin with E1, E1 joins B1 to B4. So, E1 equal to B1 B4, okay. E2 equal to B1 B4, E3 equal to B1 B2 and E4 is B2 B3 E5 is B2 B3 E6 is B4 B3 E7 is B2 B2, it is a loop at B2. Okay. So, there are 7 edges E1, E2, E3, E4, E5, E6, E7 which are ordered pairs of vertices. Now, let us say E equal to UB is a directed edge in a digraph. Okay. Then we use the following terminology: E begins at U and ends at V. Okay. U is the origin or initial point of E and B is the destination or terminal point of E. Say for example, this is U and this is B, okay, this is your edge E, okay, and the direction is UB. So, E equal to UB, E equal to UB. Okay. So, U is the origin or this is initial point of E and this is terminal point of E. So, this is terminal point of E, okay, terminal or destination point of E. V is a successor of U, okay, V, this V is a successor of U. Or we also say U is adjacent to B, U is adjacent to B, or B is adjacent from U. Okay. If U equal to B, then E is called a loop. Now, the set of successors of a vertex U is denoted by this U and it is the set of all B belonging to B such that there exists an ordered pair of vertices U B belonging to E. Okay. So, this set consists of all those B belonging to B such that there is an edge from U to B, okay, and B is the successor of then U, B is the successor of U. So, this is successor list of U or adjacency list of U. This set is called as successor list or adjacency list of U. Now, describe the diagram of digraph G equal to GBE in the figure below. Okay. So, let us see what are the vertices here. First we describe the vertices. So, B is the set of vertices here. Vertices are A, B, C, D. Okay. And then set of edges. Edges are E1, E2, E3, E4, E5, E6, E7, okay, E8. So, E1, E2, E3, E4, E5, E6, E7, E8. Okay. Now, what is E1? E1 is AD, E2 is BA, E3 equal to BA, E4 is DB, E5 is BC. Okay. E6 is DC, E7 is BB, it is a loop, okay, and E8 is equal to CD. We had earlier defined parallel edges. Okay. Parallel edges were those edges which were which had the same which joined the same points. Okay. Here A and B, okay, these two join the same points B and A, but here in the case of directed graph, okay, those edges are called parallel which join the same points and their directions are also same. Say for example, here E2 and E3 they join B and A, and moreover their directions are also same. Okay. So, you can see E2 is BA, right, and E3 is also BA. So, E2 and E3 since they join B and A and their directions are same, so they are parallel edges. So, E2 and E3 are parallel edges. Now, in the case of E6 and E8, okay, E6 is DC, E8 is CD. Okay. Although they join same points C and D, but their directions are opposite. Okay. E6 is DC from D to C, E8 is from C to D. So, E6 and E8 are not parallel edges. As we said earlier, E7 is BB, so it defines a loop at B, it gives a loop at B. Now, let G equal to GB be a directed graph, okay, and B dash be a subset of B. Okay. B is the set of vertices of G. Then E dash is a subset of E such that suppose E dash is a subset of E such that end points of the edges in E dash belongs to B. Okay. The end points of the edges in E dash belongs to B dash, then H B dash E dash is a directed graph and it is called a subgraph of G. Okay. If E dash contains all the edges in E whose endpoints belong to B dash, okay, then we say that H B dash E dash is a subgraph of G generated by B dash. Now, let us say this example. Let us look at this. Consider the graph G equal to GBE in the figure given below. Let B dash be equal to BCD. Okay. So, BCD. See what is B here? B is equal to A, B, C, D. And what is E here? E is equal to E1, E2, E3, E4, E5, E6, E7, E8. Okay. E1, E2, E3, E4, E5, E6, E7, E8. Just now we had studied this example. Okay. Now, B dash, what is B dash? B dash is BCD. Okay. We are given B dash equal to BCD. So, clearly B dash is a subset of B. Okay. Now, E dash consists of E4, E5, E6, E7. E4, E5, E6, E7, okay, and it is a subset of E. E consists of E1, E2, E3, E4, E5, E6, E7 and E8. Okay. So, E4 is DB. Okay. E4 is DB, BC is E5, BC is E5, DC is E6 and BB is E7. Now, we have to show that H B dash E dash is the subgraph of G generated by the vertex set B dash. Now, let us go to the definition of subgraph of G when generated by the vertex B dash. Here we say that H B dash E dash is a directed graph and it is called a subgraph of G, that we have seen. B dash is a subset of B, E dash is a subset of E. So, H B dash E dash is a directed graph and it is a subgraph of G. Okay. So, H B dash E dash is a subgraph of G. Because E dash is subset of E, B dash is subset of B. Now, we have to show that it is subgraph of G generated by the vertex B dash. So, let us see how we define that. H B dash E dash is called the subgraph of G generated by B dash if E dash contains all the edges in E whose end points belong to B dash. Okay. So, let us see what is B dash here. B dash is BCD. Okay. BCD are the end points B, okay, C, D. Okay. So, we say that E dash contains all the edges in E, okay, whose end points belong to B dash. Okay. So, E dash contains all the edges in B. E dash contains, now E dash contains what edges? DB, okay. E dash contains DB, BC and then DC and then BB. Okay. So, end points of these vertices are, you see, end points are here for this edge, end points are D and B, for this end points are BC, B and C, for this end points are D and C and for this end points are B. Okay. So, end points are B, C, D. Okay. The end points here, end points of the edges, okay, of E dash, end points of the edges of E dash are B, C, D, okay, and they clearly belong to which belong to B dash. Okay. So, H B dash E dash is the subgraph of G generated by the vertex set B dash. Now, let us consider this graph GBE, okay, where B is the set of vertices B1, B2, B3, B4, B5, B6 and E is the set of edges B1, B3, B2, B1, B2, B3, B2, B4, B3, B2, B3, B4, B3, B5, B4, B6, B5, 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 B4, B6, B2. So, that means at this B4, 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 B6, oh okay, no, this B5, B5, this B5, B5 gives us a loop at the vertex B5. Okay. Now, let us draw the diagrams of the subgraphs of G generated by B1, B2, B3, B4. So, B1, B2, B3, B4 is clearly a subset of B. Okay. Clearly, B dash is a subset of B, this B dash is a subset of B. Okay. We have to draw the diagram of the subgraphs of G, okay, generated by B1, B2, B3, B4. So, we have to find all those edges of E, okay, whose end points are B1, B2, B3, B4. Okay. So, B1, B3, okay. We will take B1, B3, okay. Then we will take B2, B1, then B2, B3, then we have B2, B4, then we will have B3, B2, then we have B3, B4, and then we have yeah. So, let us take E dash to be equal to this. Okay. So, E dash consists of those edges whose end points belong to B dash, and therefore, the graph of graph G of B dash E dash will be the subgraph of GBE generated by B dash, okay, generated by B dash, and its figure could be like this. You see this figure, look at this figure, it satisfies all these the edges here are nothing but the edges of E dash. So, you can see a B1, B3, okay, this is B1, B3, okay, B2, B1, so this is B2, B1, then B2, B3, so we have B2, B3 here, this is B2, B3, then we have B2, B4, this is B2, B4, then we have B3, B2, so this is B3, B2, this one, okay, and then we have B3, B4, okay, so this is B3, B4, this one. Okay, so, this graph, okay, this graph is the graph which is generated by the vertices B dash, B1, B2, B3, B4, consisting of B1, B2, B3, B4. Okay. So, H B dash E dash, okay, H B dash E dash, this is H B dash E dash, this one, and it is generated by B dash, is the subgraph now. In the other example part, okay, B dash is B2, B3, B4, B5. So, let us consider those ordered pairs here in E whose end points are B2, B3, B4, B5. Okay. So, B2, B3. Okay. So, we can take this one B2, B3. Okay. Then we can take B3, B2. We can take B2, B3, B2. We can also take B2, B4. Okay. And then B3, B4. We can consider this one B3, B4, and then B3, B5. This is B3, B5, and then B5, B5 we can consider. Okay. B5, B5, and then B5, B4 we can take. Okay. Yeah. So, 1, 2, 3, 4, 5, 6, 7. Okay. There are 7 edges. Okay. And a graph showing these edges and vertices B2, B3, B4, B5 is this one. Okay. So, B2, B3, B4, B5. Okay. Now, let us see the edges of this graph are these edges B2, B3, you see B2, B3, okay, B2, B3 here. Okay. So, here E dash for part B, okay, for part B E dash is B2, B3, and then B2, B4, then we have B3, B2, then we have B3, B4, then we have B5, B3, B5, and then we have B5, B5, and B5, B4. Okay. So, B2, B3, okay, B2, B3 is here. Okay. Then B2, B4, B2, B4 is there, then we have B3, B2, B3, B2, this one. Okay. So, B3, B2 is there, B3, B4, B3, B4 is there, okay, B3, B5, this is B3, B5, and then we have B5 B5, this is B5 B5, okay, and then B5 B4. So, this one, okay. So, this is the graph of H B dash E dash, okay. It is the diagram of the diagram of H B dash E dash, this subgraph of G generated by B dash. Now, suppose G is a directed graph, okay. Suppose G is a directed graph, the out degree of a vertex B, the out degree of a vertex B of G written as out degree, okay. V is the number of edges beginning at B, the number of edges which begin at B, okay, they give us the out degree of V, and the in degree of V is written as in degree, okay. So, this is the number of edges that are ending at B, okay. So, out degree is the number of edges which begin at B, and end degree is the number of edges ending at B, okay. The sum of the out degrees of the vertices of a digraph G equals the sum of in degrees of vertices, okay. So, sum of out degrees of the vertices of a digraph is equal to the sum of in degrees of the vertices, and it is also equal to the number of edges in G, okay. Now, let us see how we prove this. Since each edge begins and ends at the vertex, okay. See, you take any vertex, okay, a vertex begins and ends at vertex, okay. Any edge begins at a vertex and ends at a vertex, okay. So, the sum of the in degrees and the sum of the out degrees must be equal to n, okay, if there are n vertices, the number of arcs in G, okay. So, now a vertex B with positive out degree, if we have a vertex with positive out degree and 0 in degree, that 0 in degree means there are no edges ending at B, okay, but there are edges beginning at B, okay. So, if B has a positive out degree and 0 in degree, it is called a source, okay. So, if you take a vertex such that the edge begin at this vertex, okay, edge begin at this vertex, there is no edge which is ending at this vertex, then it is called a source, okay, it will be called a source. And if there is a edge, there is a vertex which with 0 out degree and positive in degree. 0 out degree means you have edges ending at B, okay. No edge is beginning at B. So, this is called sink. So, if in a positive out degree is there and 0 in degree is there, then the vertex will be source, and if positive in degree is there and 0 out degree is there, then it will be called a sink. Now, consider the graph G in the given figure and discuss out degree and in degree of the vertices of G. Let us see. Let us first find the out degree of A. So, how many vertices are beginning at A? You see this vertex, okay, the vertex is this E1 is beginning at A, okay. There is no vertex other than E1 which is beginning at A. So, out degree of A is 1. In degree of A will be how much? The edges that are ending at A. So, E2 is ending at A, E3 is ending at A. So, out degree in degree is 2, okay. Now, similarly out degree of B, at B you see we have E5, E5 beginning at B, okay, E3 beginning at B, E2 beginning at B, okay, and moreover E7 beginning at B, because E7 is going like this. So, E7 actually is beginning at B as well as ending at B, okay. So, when we are counting the edges that are beginning at B, then we will count E5, E3, E2 and also E7. So, we have 4, and in degree of B will be in degree of B will be equal to in degree will be equal to now 1 because this edge is ending at B. So, E7 is ending at B. So, we have one for this, and then E4 is also ending at B. So, 2. Okay. Then out degree of C. Okay. Out degree of C. So, at C you can see E8. E8 is beginning at C. Okay. And only E8 is beginning at C. So, out degree of C is 1. In degree of C, how many are ending at C? E5 is ending at C, E6 is ending at C. Okay. So, 2. And then out degree of D, let us see how much. Yeah. So, out degree of D means E6 is beginning at D, and also E4 is beginning at D. So, we have 2 in degree of D. In degree of D will be E1 is ending at D, okay. E8 is ending at D. So, in degree is 2. Okay. So, we have considered A, B, C, D, all of them. Now, let us find the sum of out degrees. Sum of out degrees is sum of out degrees is 1, 4, 1, 2. Okay. So, 1 plus 4 plus 1 plus 2, that is 8, and sum of in degrees of the vertices of this digraph. This is 2 plus 2 plus 2 plus 2, that is 8. Okay. And number of edges of this digraph, number of edges. See, we have E1, E2, E3, E4, E5, E6, E7, E8. So, there are 8. Okay. So, sum of out degrees of the vertices of a digraph is equal to sum of in degrees of the vertices of the digraph, and is equal to some number of edges of the digraph. Now, labeled directed graph. If the arcs are and or vertices of a directed graph are labeled with some kind of data, okay, then the directed graph is called a labeled directed graph. So, if the edges are vertices, okay, are both of them are labeled in the case of a directed graph are labeled with some kind of data, then we will call the directed graph as a labeled directed graph. Now, let us consider the 3 states shown in the digraph in the given figure given below. So, let us see this one. Okay. You see this digraph. Okay. Here the edges are labeled. Okay. Edges and the vertices are labeled. This vertex is New York, this vertex shows Michigan, this vertex shows California, and these edges are labeled with 8%, 12%, 4%, 5%, 14%, 10%. So, it is a labeled directed graph. Okay. Now, let us see. So, what is the problem? Consider the 3 states shown in the digraph in the figure given below. The numbers assigned to each arc represent the percentage of a state's population that immigrates the initial state to the terminal state each year. Thus, 10% of the New York population, you see 10% of the New York population moves to California each year. You can see here, you see this one, this age, okay, this age, okay, shows that 10% of the New York population immigrates to California each year, and 14% of the California population immigrates to New York each year. Okay. So, it is a labeled directed graph. Now, let us answer these questions. What percentage of population of Michigan moves to New York each year? Okay. So, let us say Michigan to New York, Michigan to New York, okay, this much. So, 8%. Okay, 8% of the population of Michigan moves to New York each year. Then what percentage of population of California moves to either New York or Michigan? So, California population moves to New York. California population moves to New York is 14%. California to New York, 14%. and California to Michigan. We have California to Michigan 5%. So, percentage of population of California which move to New York or Michigan is 19%. Okay. So, total is 19%. 19% of California population moves either to Michigan or to New York each year. Now, to which state does 10% of the population of New York move each year? Let us see, from New York 10% population moves to New York to California. So, 10% population of New York moves to California each year. So, this state here is California. So, that is the end of my lecture. Thank you very much for your attention.